Hi, welcome to the video solution for Edexcel IAL Physics. This is Edexcel IAL Unit 1, new specification and the third video of this past paper, third and the last. So let's start. Question number 17. The diagram shows a climber on a rock face. A rope is kept firmly anchored by a person on the ground and passes through a smooth loop to the climber. The climber slips and falls a short distance as shown. This is the climber at the ground. Another climber was there and falls here. So this is the loop. So this is height of fallen. The fall factor is used by climbers to estimate the severity of climbing fall and is given by fall factor is equal to height fallen before rope begins to stretch and total unstretched length of the rope. So a climber slips and falls with a fall factor of 0.8 before coming to rest. The energy from fall is absorbed by climbing rope. The maximum strain in the rope is 9%. Show that the maximum force acting on the climber due to the rope is about 10,000 Newton. Assume the extension of the rope is proportional to its tension. Total unstretched length is given and mass of climber is also given. We need to find the force when the climber is falling, force due to rope. We need to find force due to rope. So it's all about falling person, energy absorbed by the rope. That means if you see energy during strike, so energy is equal to half of F delta X, and this is the force that we need to figure out. So what is going on in this whole situation? First, when climber falls, it keeps falling till here, suppose, and this is the position. Suppose I'm just dividing this whole height into two interval. This is the height I am assuming when the climber falls and rope begins to stretch, and then this is the further height fallen when the rope is stretching. So we need to find gravitational potential energy in two different scenarios. One is without stretching, and let's call it H1 and then H2, and this H2 would be the height which is the equal to the extension of the rope. So clearly, if you figure out GPE, I'm calling it GPE1, when the climber is falling and it keeps falling and falls when the rope starts to stretch. So GPE1 would be equal to MGH1. Why? We don't have H1, but we are given fall factor and we are given a total unstretched length. So we can figure out how much height before rope begins to stretch. So we can figure out H1. So we can do is like 0.8 is equal H1 upon 15. So H1 is 12 meter. This is the height fallen before a rope begins to stretch. So this is 12 meter. We can put 12 meter here, and mass is 71 at the bottom. G is 9.81 into H1 is 12. So you have a gravitational potential energy in this interval, which is 8358 joule. So this is the energy, and now we need to find the extension when the rope is stretching, and this extension is equal to second height when it is falling. So extension is delta X is 9% of 15, which is the original length. So delta x is 1.35 meter. This is the extra height when the climber will be falling when the rope is stretching. So we can find next GPE change or GPE loss, GPE2, again 71 times 9.81 times 1.35. So 1.35. So we have a GPE2 which is equal to 940.3 joule. So the total GPE loss or total gravitational potential energy loss when the person is falling is GPE1 plus GPE2, and this total GPE loss is equal to energy gained by the rope. So I can say that energy gained by the rope E is equal to GPE1 plus GPE2. That is half of F delta X is equal to 8358 plus 940.3. Clearly delta X is again given. We have found 1.35. You can substitute delta X here and you can figure out F after simplifying or after solving this for F. So F will be around 13,775.25 Newton. So that's how you can say. So around 13.7 thousand. So 13.7 thousand. If you wish, you can say 13.7 thousand or 1.4. So it is around 13,000, which is about 10,000 Newton. That's the answer. A new climber suggests using a longer length of rope between the loop and the climber, as this would absorb more energy after all. So climber is saying that we should use a longer length because due to large length it will absorb more energy. Comment on the suggestion. So if the length is larger or long length is absorbed, sorry, if the longer rope is used, then the climber will be falling to the greater depth or height. So the climber will gain more velocity, moving at the higher velocity, and we need large amount of force in order to stop or in order to decelerate the climber. So that's not a good idea. Part B, climbing rope. Climbing rope manufacturers recommend that ropes are replaced every 5 years. The force extension graph up to breaking point for 1 meter length of a rope when new and after 5 years are shown. So this is force extension graph of the two ropes, new and the old rope after 5 years. So comments on manufacturer's recommendation. Your answer should include calculation. If you see the graph and you can see that the area under the graph of the first rope or the new rope is larger than the area under the old graph. That means the new rope absorbs more energy, so that's a good thing. And moreover, the graph for the new rope is higher than the old one. That means the stiffness is higher. So new rope has higher stiffness, so required a large amount of force to break. But here the answer requirement is some calculation. So we need to find the areas under the two curves and the gradient so that we can compare their values. So let's find the area under the graphs of both of the curve. So you have two choices whether you count the each and every square under each graph, but these are a smooth curve, and what I recommend that we must choose a specific position on the y-axis to draw a horizontal line. And if you see, if I draw a line somewhere, let's suppose if I see, yes, I'm drawing a line, horizontal line till that point, and this is the point where the graph is ending. And meaning, if you see, so if you find area of this rectangle, area of that rectangle, so that area will include the area above the curve that we don't need, but I am excluding area under that section. So this area will compensate with this excluded area. So I'm including that area and excluding this area. So area of this rectangle can be considered as estimation of the area under whole curve, and it's easy to find the area of that curve. So A1, or it's easy to say AN, area under the new rope curve, which is equal to, this is 5,506, so 6,000 times the x-axis value, so 0.1 and 0.1105, and this is 0.135 or 0.135 around, or 0. Yeah, it's better to write 0.135. So you multiply 0.135 and you have area under this graph is 810 joule. Similarly, you can do area of the old graph. So you can say, let me just clean. So remember this number 810. Now I'm going to find the area under the graph of the old rope. Again, I will use the same technique, the horizontal line that divide the graph into two parts. One is above and the one is below. So if you draw a horizontal line for a lower graph till here and then complete the rectangle, so you can see I am including this area which I don't need. I need the area under the curve, but I am excluding this area. So the area of this rectangle again will be area under that curve. So from the graph, this is 4,000 and this one is 0.15 and 0.185. So I can find area under old curve, which is AO. So 4,000 times 0.185, which is equal to 740 joule. Clearly, AN, which was 810, is greater than AO. So the old rope is going to absorb less amount of energy. That's why it is good to replace the rope after 5 years. Moreover, it's just not about the area absorbed, but we also need to find amount of force that need to break the rope. So for gradient, you have two choices. You can choose a point anywhere on the graphs and then find the gradient, or you can choose a single point and compare the gradient of that simple the same amount of force, gradient of the two rope. That's what I'm doing now. So I am choosing the best point that I am choosing. So is 5, yeah, here is the point. This is the point that I'm choosing on both of the graphs, so that I can find the extension easily. So gradient for new rope will be 5500 divided by 5500 is that amount of force divided by the extension at that moment, and this is equal to 0.075. So the gradient will be 7.3 into 10 to the power 4 Newton meter inverse. This is the stiffness of the new rope, and gradient of the old rope would be equal to 5500, same amount of force but at a different extension, different point. So 0.135, the gradient will be 4.1 10 to the power 4 Newton meter inverse. That means clearly gradient of for the old rope is less than the gradient of new rope. That means the old rope is going to break. Old rope can break at a small amount of force. So that's the comments on manufacturer's recommendation. Question number 18. When water vapor in the atmosphere cools, it condenses, forming tiny drops of water. These drops increases in size by colliding with each other and fall back to the ground as rain. As a raindrop falls through the air, it eventually reaches its terminal velocity. The upthrust on the raindrop can be considered to be negligible. Explain what is meant by terminal velocity of the raindrop. Your answer should include a free body force diagram for the raindrop when terminal velocity has been reached. In general sense, whenever an object is falling through a fluid or any liquid or whatever, so the object falling through a fluid experiences three forces. Number one is the weight acting down, and upthrust acting upward always, and the drag force depending on the direction of motion. But object is falling downward, so drag force acts upward, and this drag force decreases with the velocity until sum of these two forces equals to the weight. So if W is equal to U plus D, then we say at that moment acceleration becomes zero. So the velocity remains same or constant after that moment, and that velocity is called terminal velocity. And in this case, for the raindrop, they are saying that the upthrust can be negligible, so you ignore the upthrust, so that means W is equal to D. So you say that as raindrops falls downward, so drag force increases. When W equal to D, then drops falls with the constant velocity called the terminal velocity. The air resistance F acting on a raindrop traveling at a velocity v can be determined using the expression F equal to 0.45 rho a v square, where a is the cross-sectional area of the raindrop, rho is the density of air. Calculate the terminal velocity of a spherical raindrop of radius that. Density of air and density of rainwater is given. So we need to find the terminal velocity, which is in this case this. So we know that at terminal velocity, this air resistance is in fact drag force, and at terminal velocity, the drag force F is equal to the weight. So you can rewrite this equation as 0.45 rho A V square is equal to mg, m into g. But we don't have mass of the raindrop, but mass of the raindrop can be figured out using density and the volume of the raindrop. So because we have two different rows, this is for that mass I'm going to use density of the raindrop, and in this expression this row is density of the air. So I am writing here as A, density of the air, and this m can be replaced with density of the raindrop and the volume. So you can rewrite this equation as 0.45 rho A. This is the capital A, area of the raindrop, so pi r square. V square is the velocity that we are going to find. M is the mass, so density of the raindrop, volume of the raindrop into G. So 0.45 rho A pi r square V square rho r VR, volume of the raindrop, which is spherical, so 4/3 of pi r cube into G. Clearly pi and pi cancelled, r square and r square gone, and now we can make V as a subject or V square as a subject. So V square is equal to 4 rho r into upon G divided by 3 rho A into 0.45. You can plug in all the values. Rho r is this, r is the radius, G is 9.8, rho A is the density of the air. And then when you solve it, and after taking a square root, so V velocity would be equal to 6.96 meter second inverse, or you round it off to 7 if you wish. Some plants have adapted to high rainfall by having a specialized shape and waxy leaves. This allows rain to slide down a leaf and off the end as a series of drops. A drop of water slides off a leaf as shown. Add the diagram to show the position of drops at regular interval of time. The first two positions have been drawn for you. So you need to draw position of the drop, and it's a typical question of a projectile when drops fall downward. So due to increase in vertical velocity, vertical distance increases, but horizontal distance stays same. So when you drop the next drop, so it should be slightly at higher height, or the depth of the third one should be greater, like this, and then like this, and then so on. So you can you need to take care of the horizontal distance. This distance must be same, something like this. So that's how you see the situation. Water falls from a leaf at a steady rate of 5 drops per second. As each drop reaches the ground, there are 4 drops above it in the air. Calculate the height of the leaf from the ground. It can be assumed that the drop at highest position has just left the leaf. So I am redrawing the diagram according to the second part. It is because they say that when each drop reaches the ground, there are 4 drops above the air. So what I am doing is let's suppose something like this. So you see that when the a single drop, or you can say when the first drop reaches the ground, there are four drops in the air, one, two, three, four, and the rate of falling drop is 5 drops per second. This information is given so that we can find the time for fall of one drop in one interval. That means, let's suppose from here to here, this is the first interval. So how much time this drop will take to reach the next position, and this is the time drop for one drop in one interval. So t is equal to 1 upon 5. So 0.2 second. This is the time when the drop, this is the time that taken by the drop to cover one interval only. And they are saying when the drop reaches the ground, four drops are already in the air. So how many intervals do we have? We have four intervals. So the total time taken by this drop should be t is equal to 4 times of 0.2. That means 0.8 second. Now we have a time, so we can figure out height, the vertical height covered or traveled. And as this is vertical motion, we are going to use S is equal to ut plus half at square, where S is the height and u is the initial vertical velocity. In this case, the water droplet is moving only horizontally. We don't have a vertical motion, so this u is 0. So finally, the height h is 0.5, because this term is gone because of 0. So we have half, meaning 0.5 into a, acceleration 9.81 times t square, 0.8 whole square. So h is equal to 3.14 meter. Thank you very much. I hope you enjoyed the solution of this past paper. Thank you.